Yeah, this one. Yeah, we have 4 presentations. The first one will be done by Duriclance company. It's a company here in Quebec City, which will be presented by Jean-Luc Néron, followed by Theo from COPL, and then Mathieu Bellec from University of Bordeaux, in fact, from Nice. And finally, we changed our programmation because the last one declined because it had another meeting. Then we have been happy today that we'll get Lexian Wang from Huawei will give us a fiber for future optical telecommunication. And of course, in the last 10 minutes, we would like to show you the about the laboratory facility, which include glass preparation, drawing fiber, and I hope they will enjoy the facility, and you are welcome to use at any time our facility here at COPL. I don't like to change our planning, and we have a lot of exciting presentation. Please, Jean-Luc, if you can start the first talk.
Yeah, hi everyone. I will just prepare to share my screen. This one. So I don't know if you can see my screen correctly.
Yes, perfect.
Okay, thanks. So hello, my name is Jean-Luc Néron from the company Direct Lenses. I will make a short presentation on the use of fiber optic for neuroscience research to record and manipulate specific neural activity with light. So here is a short plan of the presentation. So I will do a short presentation of the company, and then I will shortly explain how the light is used for neuroscience research. And I will focus on 3 optical techniques. First will be optogenetics, and with some detail on light source and optical fiber. So some details on what are the characteristics of the light source and optical fiber that are used for that technique. And I will also present fiber photometry and miniature fluorescence microscopy, which are optical recording technique for brain research. So direct lenses have been found in 1995 in Quebec City in Canada, and the mission of the company was to commercialize a patented gradient index cylindrical lens, which was mainly for laser diode collimation. But it's interesting to say that the construction of that lens is really similar to an optical fiber. Actually, it's really the same process of manufacturing, except that instead of using injecting the light inside the fiber, we use it sideways to act as a cylindrical lens. Then back in 2007, the company started to make some custom requests for neuroscience lab where they needed some specific equipment to start using optical fiber with chronic implant with freely moving animals. So we started with some custom requests, but with the increasing demand and increasing popularity for those techniques, we now have a wide range of product to address the research need in that field. We now produce specialty light source, optical fiber rotary joint, fiber photometry system, miniature fluorescence microscopy system, and much more. All optical fibers, cable, and implant for that research that we will discuss in this presentation. So the use of light in neuroscience. So the most commonly use of light in neuroscience is for microscope illumination, either for fluorescence illumination, but typically on large scale microscope to try to map the brain, or to understand the brain, but more in slice or head fixed animal. In the last 2 decades, the neuroscience research did important advance with the development of new sensor that use the light, so to control or monitor the neural activity with techniques like optogenetic fluorescence imaging of neural activity. So we will discuss that a little bit more in detail. And the main advantage of using optical sensor instead compared to electrophysiology is the ability to modify only a specific population of cells or of neuron to make them only a very specific population, to make them sensitive to the light stimulation, either by viral injection or genetic modification. And this allows very tailored interrogation and manipulation of neural circuit. And maybe one thing I should mention, I'm not a neuroscientist or a specialist in neuroscience. I'm more a specialist in optics, but that have some experience with the years trying to help researchers to do what they want to do. So I will give some information on the neuroscience research, but I'm not an expert in that field. So I just want to tell that. So the first technique that we'll discuss is optogenetics that use the light to stimulate or inhibit neural activity of genetically modified neuron that are modified to become sensitive to a light stimulus. And to deliver the light to the neurons, there is a different possibility, but for sure the optical fiber is a good way to bring the light into a specific brain region, especially when you work with the freely moving subject. Also, another characteristic, researcher want not only to study the cortex or the first layer of the brain, but they also want to go deeper to study different brain area. So to do that in a in vivo freely moving animal, you can use an optical fiber that you can insert. It have to be a small fiber, but that can be inserted into the brain either for acute experiment, or it can also have a connector and remain chronically implanted to do experiment for several weeks or months. So yeah, to have access to the brain region, as you can see in this picture, researcher does implant electrode, but also optical fiber, or for imaging, so for the microscopy, if you want to get images, you can also use a gradient index imaging relay lens of small diameter, because you don't want to create too much damage to the brain itself by inserting fiber. So yeah, so there's some challenge related to work with optical fiber. One is to maintain a good optical transmission and stability, especially when you work with freely moving animal. It sometimes requires to have we call it optical fiber rotary joint. So it's a optomechanical device that will allow the fiber to rotate, and so it gives to the animal more. It removes the tension from the cable when a cable is connected to a freely moving animal. And you also want to minimize the impact on the animal behavior. So you need to use very tiny, small fiber with a very lightweight jacket. But you also want to have some protection to avoid the animal to break the fiber. So there's always some compromise to do when using optical fiber in those experiments. And you also want to minimize the brain damage, but you also want to cover as large brain area as possible. In fact, in ideal world, you will like to have access to the complete brain area, but it's not possible because you will by inserting fiber, you will create too much damage. So there's different strategy to try to access larger area with multiple small fiber, for example, but there's always a compromise to do. Yeah, here I will just speak a little bit more on the light source and optical fiber that are used for that research. So the important criteria for the light source is the wavelength, because each sensor or opsin have a specific response to different wavelengths. So you have to make sure that your light source have the right wavelength. And you also need to make sure that you will get the right optical intensity at the fiber tip. So it have to be above a certain threshold to get the optogenetic effect, but you don't want to get too high intensity to avoid creating damage to the brain. So because there's a lot of absorption in the brain, so if you bring too high intensity or too much power, you will create heat or permanent damage to the cells just in front of the fiber. Another important characteristic of the light source, you have to have a good modulation capability. Typically, the optogenetics will deliver a sequence of pulse with different frequency. So the light source it cannot be a continuous light source. It have to have the capability to be modulated. And you want a good power stability with time to ensure that all the experiment you will do along several weeks will get the same optical power, so in the same condition. Other aspect to consider when selecting the light source and the fiber. So depending of the type of fiber, you may prefer laser or LED light source. Again, it also depends on the power. Depends, yeah, if you want to do a single site or a lot of experiments are made with two fiber, one at each side of the brain, or some people also have insert multiple fiber at the same time to cover very large or complex brain circuit. And then when you have multiple fiber, you have to choose if you want common illumination of all the fiber, or really independent control of each site, which add to the complexity of the setup. But if that's what your research is asking for, then you have to do that. And then depending if it's a chronic implant or an acute experiment, it can also change the characteristic of the fiber. Typically with acute experiment, you can use a smaller fiber to minimize the damage during the insertion because you want to get the effect immediately. For chronic implant, typically you will use a slightly larger fiber because you will cause a bit more damage to the brain, but you will leave the brain to recover for weeks. So the advantage of using a larger fiber is that you will cover a larger area, so you have more chance to have an effect on larger population of cells. And another aspect to consider is if it is to work with freely moving animal, then you may want to add the optical fiber rotary joint to remove the stress in the cable. Another aspect to consider is that the brain or the gray matter have a strong absorption and scattering for the visible light. So the penetration of light in the tissue is limited, and that's why if you want to illuminate a relatively large zone, you sometimes have to increase the diameter of your optical fiber to make sure you cover the volume of tissue that you want to illuminate. Higher numerical aperture will typically help to spread the light to a larger cone at the output, but still those fibers are often more fragile. So it's possible to use, but there are some mechanical constraint to use high-NA optical fiber for brain implant. And here is just a few example of light simulation in brain tissue with different tip of optical fiber, because you can shape the tip of optical fiber, especially when you use a larger diameter fiber. Having it with an angle or a cone or a taper will help to reduce the damage when you insert in the brain tissue. So instead of pushing the gray matter, you're really cutting into it. So it helped to reduce the damage. But and so we do some simulation to show how the light is going out of the fiber to give an idea to the researcher where they should target the tip of the fiber in the brain. And there's also the possibility to have the mirror on the facet on the really tip of the fiber to get side illumination, depending which brain region and from where you're trying to access. Sometimes it's useful to use a mirror tip. So another technique, so the optogenetic was more about modifying the behavior of the neuron with light. In fiber photometry, you just monitor the activity of the neuron that have been labeled with the fluorescent reporter to get fluorescence when the neuron is active, or when there's a release of typically let's say the most popular sensor for optical imaging of neural activity is a calcium sensor. So when the cell is releasing calcium, the membrane became fluorescent, and then you collect this change of fluorescence with an optical fiber. So you have a signal that will increase when the neuron is releasing calcium. But there's also now different other sensor to measure dopamine exchange but as I said, I'm not expert in that field, so we're trying to help researcher, but they typically explain us what they do, and we try to find the optical solution to help them doing that. The advantage of fiber photometry is that you can record neural activity of a very specific population of neuron, compared to electrophysiology, where you will collect the neural activity, but from all the neuron in the region where the electrode is. But with the optical technique, you can really target a specific cell population that are labeled with the fluorescent marker. It is compatible with deep brain fiber optic cannula. So you can chronically implant the optical fiber in the region you want to monitor, and then for several weeks you can measure the fluorescence signals. It have relatively low impact on the animal, on freely moving animal, because the size of the connector that you have on the animal is very light, very small. The only restriction is the cable, but again, it's also a relatively small cable, and I cannot say that it does not affect the behavior, but you can have relatively normal behavior with the for a time restricted, very specific task behavior experiment. Also, fiber photometry allow for multiple site recording, a little bit like optogenetic. You can have multiple fiber implanted chronically in the brain of animals. You have very high temporal resolution. It's limited by the detector that you will use, but if you need very fast, if you have a very fast sensor, you can use a PMT that will give you kilohertz bandwidth. And you again, with the detector, you can have, if you choose a very sensitive detector, you will have a high sensitivity to use very low optical power to reduce the bleaching effect, and any effect. In principle, you want to monitor the activity, so you need light to get fluorescent signal, but you want to use as low light level as possible to reduce the impact of the light you deliver in the brain tissue. The disadvantage is, since you use a optical fiber, you are not imaging, so you don't see a single cell. You are averaging on the diameter of the optical fiber. You also have limited sampling depth. It is 1 photon fluorescence, so you're measuring, let's say, the layer of neuron which are maybe about up to 150 micron from the fiber. Further away, you have too much absorption, and you don't get the signal. So it's relatively limited sampling volume, but it's still useful for many research. And even if we want to make it as small as possible, it's still invasive chronic implant, because you have to insert the fiber in the brain. So it's and also another disadvantage is that you have to use a marker. So you cannot do that in a normal animal. So you have to. It's an animal that have been either modified genetically, or you insert a virus to get to mark the cell. So that add to the complexity of the technique. So the Reclinators offer all the system to make fiber photometry for the researcher, going from the optical fiber implant to all the cable, the optical fiber rotary joint, the fluorescence cube, and the data acquisition electronics and software. And it's possible to combine with other technique as optogenetic, electrophysiology. You can also have simultaneous drug delivery to in, let's say, in another brain region, to see the effect on different other brain region. And it's most of the time it's also combined with video tracking to monitor the behavior of the animal and correlate the behavior with the neural activity. Another technique is miniature fluorescence microscopy, which use the same sensor as fiber photometry, with the difference that now you are doing single cell imaging. So you really do imaging, and you have single cell resolution. So instead of implanting optical fiber in the brain, we implant a gradient index lens that reimage the a certain layer of neuron inside the brain. Uh, so to reimage that above the skull of the animal, and then there's a very small fluorescence microscope which is attached to that fiber to reimage this on image sensor. And this can be used on freely moving animal. um, uh, so that if I just follow my presentation, so the advantage is to record individual cell with single cell resolution. So you can map the spatial position of a group of neuron. In the next slide, I will show a video of the type of result we can have with that technique. And you can correlate the functional and morphological cellular activity with animal behavior. And as for fiber photometry, you can monitor the same population of cells for several weeks or months. And you can also compare two different populations of cells by using two-color fluorescence with two different markers. And it can also be combined with optogenetic, electrophysiology, or other techniques. The disadvantage is that still we try to minimize the size and the weight of the microscope, but since the microscope is mounted on the head of the animal, this microscope have a weight, so we try to keep it below 4 grams. But for a mice, so it's small for us, but for a mice it's not a negligible mass. So they have to be trained to tolerate that mass on the head. But after some training, they get relatively normal behavior. And again, as for fiber photometry, it is limited sampling depth due to scattering, and because we use single photon epifluorescence imaging. Some group now are working to offer a 2-photon miniature microscope, which allow for a better resolution and also a little bit deeper. You can see a little bit further away from the green tip, but we don't offer that product. And as any implant, the green lens is we typically use 0.5 millimeter diameter for implant, but still it's an invasive implant. And here is a video of, I don't know if it will work. No. Sorry, the video doesn't. Oh, okay. Yeah, yes, it works. So yeah, just to say, we offer the complete solution for miniature fluorescence microscopy, from the green lens implant to the microscope and all electronics and software to control and analyze the data. So here you see when there's a flash of light, it's one neuron that release calcium. So you really see neural activity with single neuron. So all the blue circle are a specific neuron that have been detected by the post analysis algorithm. And unfortunately, I cannot explain the specific experiment we did to get this data, because again, I'm not the expert in the biology. So that is the end of my presentation. Just a short summary. After a short presentation, I presented 3 optical techniques that use optical fiber in neuroscience. So optogenetic, fiber photometry, and fluorescence microscopy. So that's it for my presentation. Thanks for your attention.
Do we have any questions? You have to come here. Sorry. We have one question here. Diego is just coming.
Mm-hmm.
Sorry.
Can you say?
Yeah.
Okay. Thank you for your presentation. You were saying that larger diameter would be more damaging for the cells, right?
Mm-hmm.
But if you decrease the diameter, isn't it the light will be more concentrated? No.
Yes. You have to adjust the power to avoid too high intensity.
Okay. And also the material, for example, the cover we use for the fiber, and also the fiber itself, isn't it damaging to the cells, the interaction, the physical interaction between the fiber and the brain, for example? How is it?
For sure, it distracts some of the structure. Typically, you will target this very specific zone, and you will insert the fiber and all the layer that you will cross before that zone. You will affect them in a way, and you try, and in some case you will hit a brain vessel, and it will make a hemorrhage, and it's not good. You want to avoid that. But you will typically you want to cross. So you try to avoid, let's say, zone that have very important role in the life of the life of the animal. But for sure, it's an invasive technique. Deeper you want to go, more damage you will create. So it's true that you can go deeper when you use an optical fiber, but still you will cause some damage. So you have to be very careful of which structure you are crossing, and what is the damage you do to the animal, to make sure that the effect that you see is not caused by the damage you cause by adding a fiber in the brain.
Okay, thank you.
Okay.
I'm just checking if we have any question in the chat. Doesn't look the case. So if we don't have any more question, we can thanks again, Jean-Luc, and so can move on to the next presentation.
Okay, thanks.
Okay. So I guess you can see my screen right now. So hi everyone, good morning, good afternoon. I'm Theo Guerine, postdoctoral researcher under the supervision of Professor Younes Messadek and in collaboration with Professor Real Vallée. And today I will give a talk about our recent analysis that we made in medium-infrared Germano-Galate glasses, considering their fiber drawing and direct laser writing. So here are listed some miniaturized device criteria. And so, of course, right now, when we want to develop a new device, we want it to be smaller, cheaper, more reliable, more efficient, less raw matter consuming, and also less energy consuming. And one way, or the most common way to do so, is through some lithography techniques, database that follow the Moore's law, the Moore trend. But what has been published recently in 2016 in Nature is that the Moore's law will go to an end, but not at first from a technical issue, but rather from an economic issue. And so in this dynamic, we need to find some cheaper alternatives. And one photonic miniaturization alternative is the multi-structuring of material. So it helps to increase the sophistication of our device, but it's far away to be mature yet. So first, what we call the classic material is when we can associate one property to one functionality. So for instance, the absorption to the filtering, the index contrast to the guiding, the index spatial contrast to the focalization. But when we talk about a multi-structure material, actually, it's a combination of several functionalities. So let's take, for instance, a bundle of optical fibers. The main goal, the main mission of fibers to guide light. We can micro-structurize the fiber as for photonic crystal fiber to enhance some properties, to generate some others. And recently, it has been published that you can also fabricate a metal lens at the fiber tip, allowing a functionality of focalization. So the idea beyond that, at the end, is actually to miniaturize a laboratory in a fiber. And if we and to do so, the idea is to be able to fabricate some optical components, some components in general, like microfluidic tubing, Bragg gratings, waveguide, macro holes, etc. And so as for the light bond chip, we want the system to be compact with using low volume sample, which can be used, we can be processed very fast. But the interest of the light beam fiber is that we can increase the complexity and the geometry. So a new approach that has been developed for 25 years now of multi-structuring of materials is based on the femtosecond direct laser writing. So thanks to multi-photon absorption, it allows the volume 3D modifications. And there is a big requirement here. We must use a transparent material with good optical quality. So that's why we are working with glasses. And also glasses are really well known to be easily fabricated in shapes. So first, let's focus on the multi-photon absorption. So on the left, you have the cross-section of one material. On the right side, you have the energy level of this material. And so if you excite your material with a linear absorption, there is an excitation of your electrons, but the modification is non-localized. But now, when you have multi-photon absorption, actually, the modification is no longer non-localized, but rather localized. And to do so, we must use a laser allowing a high concentration of photons at the same time and place. So I will not, I think everybody knows the definition of glass, but through the Sentinel-9 program, we want to monitor some climate active gases in the Arctic. And so if we have a look on this very interesting graph, you will see that above 3 micron, we have the fundamental absorption on the dimethyl sulfide, the methane, the carbon dioxide, and nitrous oxide. So that means that our glass family that we want to work with should have a mid-infrared optical transmission at least up to 6 or 7 micron, can be drawn into fiber, is chemically stable, and can support the direct laser writing process. So this graph represents 4 properties. Of our glasses, there are mid-infrared transmission, there are concentration of doping elements, whether it could be transition metal or rare earth, the hardness, the HK, and the glass transition temperature, TG. So one of the most common glasses in the world that is manufactured are the silicate one, with a very important TG and hardness, but the mid-infrared transmission and doping concentration is not so good. Then in the opposite, we have the fluoride or the telluride with good solubility of doping element and a good mid-infrared transmission. Then we have the chalcogenide that even if they can be doped so much with doping elements, and they are well known to not have a very good mechanical properties and temperature properties, they still have the mid-infrared transmission above, could be above 25 micron. And then the glass unit that we are interested in here today, here are the germanogalate or gallo-germanic glasses. So why that? Because they are a hardness very close to the silicon glasses, TG that can be above 800 degrees. They also can solubilize a high concentration of doping element above 10 more %, and their mid-infrared transmission could be above or can reach 7 micron. So the more specific glasses that we are interested in today are the BGG, the barium germanium gallium glasses. And so for these 4 properties, we consider them as a highly efficient mid-infrared glasses. So how we fabricate our glasses? So through the make question technique. So just here a quick video. So we weight our precursors that we introduce in a platinum crucible. We melt them at high temperature. So here we have already pre-melted the precursors. And so as you can see, we can cast them, we can cast the liquid very easily on a metallic plate, but also on a metallic mold. So thanks, Tamar. At the end, we can fabricate some cylindrical preforms to perform the fiber drawing tests, but also some thin bulk, some parallelepipedic bulk, allowing us to perform the dark laser writing tests. So through the dark laser writing process, we need a sample that have been already optically polished that we mount on a motorized precise XYZ stages. And so if we perform this type of irradiation, so to a pristine BGG glass, we go through the technical modification. So thanks to glass densification and ionic migration, we increase the refractive index at the focal point. After an horizontal dark laser writing, what we observe is the formation of lines. So on the picture on the left, you see the profile of this modification, and on the right, the top view of this line. So in this case, we have the formation of a single track of the refractive index change. Now, when we dope our BGG with silver, we go to the type argent-top, the type A modification. So through silver photochemistry and the generation of silver clusters, we increase now the refractive index only around the focal point. So on this picture, you see the side view on the after the horizontal dark laser writing process. So it's the formation of a double wall. Actually, on the right, you have the top view of this modification. So here we have the formation of a double track of the refractive index change. So before moving on to the dark laser irradiation, I just want you to introduce how this type of glass family, the structure of this glass family. So there's two types of building blocks. The first one is the gallium tetrahedral site, which need to be compensated by barium ions. And then there's also the germanium in tetrahedral sites. So when the ratio between the barium and two types, the concentration of when the quantity of barium reached around 2 times the concentration of gallium, we have a very dense structure. But when we increase more the concentration of barium, there is a formation of non-bridging oxygen on the germanium tetrahedra. So the non-bridging oxygen are actually the formation of oxygen that are linked only now to one glass form of cations. And we have an open structure. So this type of and so when we decrease now the concentration of barium, there is the formation of gallium in a 5-fold site or 6-fold site. But we must avoid this kind of cases because actually we reach very easily the devitrification of our glasses. And so for people that are more familiar with silicate glasses, the BGG glass structure is very close to what we can find in this type of glasses. So here is the ternary diagram of the BGG glasses composed of barium oxide, germanium oxide, and gallium oxide. So we work in 2 series. And so thanks to structural analysis performed by Raman spectroscopy, we observed that in the series 1, when we fix the ratio between germanium and gallium, while we increase the concentration of barium, we observe an increase of the barium engaged with the non-bridging oxygen of the germanium tetrahedra. But on the series number 2, when we keep constant the ratio at 1 between the barium and 2 times the concentration of gallium, and while we decrease the concentration of germanium, we observe an increase of the barium engaged in the compensation site of the gallium tetrahedra site. And so for this presentation, I will only focus on this series. So here the laser that we use, so a Clark MXR laser with a wavelength at 515 nanometer, repetition rate ranging from 100 kilohertz to 25 megahertz. We fixed the number of pulses at 1 pulse per nanometer. The pulse duration is around 300 femtosecond, and the micro objective is a 50x with a numerical aperture of 0.55. So through the increase of the energy pulse, we go through several types of profile of our type 1 modification. So first is the athermal type 1 with a very straight line. Then there is some kind of onset of the thermal type 1 with the apparition of some degradation of the glass. So that's why we consider it as the type 3. Then when we increase more the energy pulse, we go to the thermal type 1. And then when we increase more the energy pulse, we have a combination of thermal type 1 plus the formation, the observation of self-organized bubble. So first I will focus on the threshold between the athermal type 1 and the type 3. So this graph represents this evolution of this threshold considering the pulse energy and the barium content for 3 different repetition rates. So first, in the 3 cases, you see that when we increase the barium content, we gain 1 order of magnitude higher for this threshold actually. But when we increase the repetition rates, we observe a decrease of this threshold, but it's kind of obvious in this case because when we increase the repetition rate, we go more and more to the thermal regime, and so this type of regime will prevail. So here is just to introduce you quickly that actually just by changing the barium concentration, we can significantly affect the glass photosensitivity. But so in our purpose, we want to generate some waveguide. It means that the profile should be as circular as possible. And so we will be more interested in the type 1 thermal regime. So we were wondering how the barium content will impact this type of regime. So in this case, we fixed the repetition rate at 8 megahertz, but we let free the number of pulses per nanometer. So from the picture from the left to the right, you see 4 glasses with an increase of the concentration of barium, and picture from the top to the bottom, you see an increase of the energy pulse. For each picture, you have 4 waveguides inscribed at respectively 1, 10, 25, and 50 millimeter per second. So for each BGG composition, either you increase the laser pulse energy or the sample translation speed. We observe a smoother delta N with less and less void, less and less bubbles. So as I told you earlier, here we observe the generation of a self-organized bubble, which is kind of original in this case because what has been published in the past was the type 1 was only an epiphenomenal during the apparition of the bubble. While in this case, it's the inverse. We have the type 1, and during the irradiation, we observe the formation of this bubble. So now the bubble formation are an epiphenomenon in this case. When we change the BGG composition now through the increase of barium content, we have less and less voids up to their complete vanishing. And so in this slide, our big assumption is based on the fact that the barium content or the barium cations help a lot to dissipate the heat accumulation via ionic diffusion. But we need to experiment that through thermal and ionic conductivities measurements. So not to summarize, but just to see it from another point of view, here's some kind of representation of the proportion of direct laser writing modification as a reservoir for both of them, so either void or thermal type 1. So for the same composition, at low energy pulse, we have the formation of a lot of bubbles. But when we increase the energy pulse, now the concentration of bubbles is a lot decreased. And it's like actually we favor only the thermal type 1. And we observe actually the same thing when we fix the pulse energy, but we change the barium concentration. So as I told you earlier, as the main aim of the type 1 modification is to guide light, we only want a smooth delta N. And so that's why we must avoid the formation of these bubbles. So in this case, by just tailoring the glass composition, we can avoid this type of bubbles, and so we will go preferentially to the glasses with high concentration of barium. So the type 1 modification is interesting where we want to generate a waveguide, but it does alter the optical glass quality, and it's kind of difficult to reach some micrometric modification. So for some other kind of optical component, for instance. So one alternative that have been developed mostly in Bordeaux is the type A modification, the type Argentum. So when we doped our glasses with silver and we perform the dark laser writing test, the modifications are only supported by the doping element. So there is no alteration of the optical glass quality, and the modification can reach a thickness about 80 nanometer. So you see here a tubular structure after a static irradiation that have been performed. And so you see that even if the height of this structure is about 5-6 micron, the thickness of this structure is about 80 nanometer. So here is just a 3D graphical representation of this static direct laser writing. And so during a linear direct laser writing, you see that we can extend in some dimensions this thin wall. And so by narrowing 2 laser paths actually, and that we can do only for now in a high concentration of barium, we can artificially decrease the distance between 2 walls. So here you have the picture for structure with a pitch about 2 micron. And we demonstrated for a structure with a pitch up to 400 nanometer, and for some of a glass composition up to 240 nanometer. And so that's kind of very interesting because it opened up a new insight for the fabrication of gratings. So my last 3 slides will be on the fiber drawing of the BGG composition. So as you may know, it's still challenging, but no one were able to fiber draw BGG composition up to 2015 due to bad surface crystallization resilience. And what has what has been succeeded by Wen et al. By modifying the glass composition through the addition of lanthanum material, they succeeded to fiber draw BGG. But last year, the COPL, we reached 2 milestones actually. The first one is to fiber draw unmodified BGG composition, either if it's rich in germanium and gallium, and also to fiber draw building casting core-clad fiber, also in the 2 type of regime. So here is the optical fiber that we use. And so there's several types of technique that we can use to fiber draw our glasses, but in this case, one of the most used, I would say. So we insert our glass preform in a preheated furnace above the GG to get the glass again softer. Then we can pull the glass and draw the preform into fiber. Here's the picture for the core-clad germanium-rich BGG. So as you can see, we have kind of a very beautiful neck down after the fiber drawing. There is no surface crystallization. When you have a look on the fiber cross-section, there is no bubble formation at the core-clad interface. There is no crystallization also. We reach one of the commercialized diameter about 125 micron, and we observe an optical losses below 5 dB per meter at 1.5 micron. But actually, that's kind of that have been. We think that we have lower losses, but we couldn't observe them due to the absorption of erbium. And here we have the picture for the gallium-rich BGG. So in this case, it's still much more tricky to fiber draw gallium-rich BGG actually. Even if we can easily handle the fiber, we observe the formation of tiny bubbles at the core-clad interface. So that was introduced during the glass casting. And these tiny bubbles helped a lot to generate some crystallization spots. And so due to that, we cannot measure the losses in these glasses. So if we want to make the most of BGG properties, so to extend the mid-infrared transmission, to increase the glass hardness and glass transition temperature, we have to reduce somehow the germanium content. And so what has been published by Haibi and Agaval in 1993, here is their ternary diagram, as I showed you also earlier. So we selected the BGG conversion with the lowest germanium content, and we fixed the concentration of barium, and so we increased then the germanium content just to see how we can stabilize the glasses to the fiber drawing process. So we work with 3 ratio, and we fixed the manufacturer parameters for the manufacture of our preform. And so in all the cases, at first we were able to draw the fiber, but after tens of meters, we observe a degradation of the preform, as you can see here with the crystallization of our neck downs. So for ratio at 2.5 and 1.8, we still have the formation of the crystallization effect, but at 1.5, we don't have this crystallization. So by keeping the same manufacturer parameters, we were able to prevent, in this case, the apparition of these crystals. So for many infrared applications, we need to introduce luminescent rare earth. But what has been shown in the preliminary work by Florent Casava at the ICMCB is that actually the yttrium is a very good choice for rare earth doping studies. So of course, the yttrium is a non-luminescent rare earth, but it helps us a lot to simulate how the rare earth will impact the glass properties without impacting the optical losses. So we fixed the ratio between gallium and germanium at 1.5, as I showed you earlier, and then we substituted the germanium by the yttrium. So we synthesize 3 glasses with 1, 3, and 5% of yttrium. And so at first we could say, okay, the glass is less and less stable. As you can see here, the delta T, so the difference between the Tx and the Tg, is decreasing. But when we have a look on the Tx peak intensity and peak area, you will see that there is 1 order of magnitude difference for this value. So actually, the glass, the derivative, the crystallization of these glasses is less and less spontaneous and is less and less slower. So we Faber draw the glasses with 3% of yttrium. So we get an improvement of our neck down actually, and there is no surface crystallization. So it's a very good sign for further works on these glasses. Here you have also the Faber profile and a section of our fiber. And since these results are kind of recent, we're not able for now to measure the optical losses. So now we conclude. So I will say we must find some cheaper alternative to what we can have to the fabrication of the devices, and light beam fiber could be one of them. In this today's presentation, I introduce you some building blocks that we can make for this light beam fiber, considering the wave guiding, the grating, and the fiber drain. So our works actually support the fact that BGG are excellent candidates for mid-infrared applications. We must consider and pay attention to the glass composition optimization if we want to combine the dark laser writing and the fiber drain. And of course, that our works must be continued. So, thank you.
Any question?
I do have a few questions. Can
Let's
I?
go.
Thank you. Hi, Theo. Thank you for this presentation.
Hello.
Can you go back, please, to where you showed the barium effect on the photosensitivity?
Yeah. I guess this one?
It's yeah, go back for type 1. Yeah, exactly. Yeah.
Sorry,
So,
can you introduce yourself, please?
oh, yeah. Hello, I'm Alain Abu Khalil. I work in femtosecond laser writing and glasses. I did my PhD in COPL and ECMCB, so I'm a bit familiar of the type A laser writing. So when you're increasing the pulse energy, when you're increasing the barium content, your pulse energy increases. I did not understand this graph. Can you please explain it for me? So your photosensitivity increases with the barium, because if it does increase, your pulse energy should be lower, or?
Yeah, the definition of photosensitivity is every time very
Different?
tricky. Yeah,
Okay.
yeah, it's I would say that in this case, actually, when you increase the barium content, you extend much more the range of which you can inscribe some modification.
Okay.
So as low barium content, actually, you see that the threshold to the type 3 is kind of low considering the pulse energy, but also there is the the window in which you can work to perform the thermal type 1 is also very reduced. Like it's much more than order of magnitude difference if we talk about only the window for the thermal type 1.
And if you go to the next slide, you were saying that you are having thermal type 1 and type 3 at the same time?
You mean
maybe
here?
Before, I don't remember which slide, but you said at some point that you have type 1 and type 3 at the same time.
But actually, it's but here it's I don't know if you see.
Yeah,
but
exactly. Yeah, this one.
Yeah, indeed. So what is kind of unusual is you go directly to the thermal type 1 to the type 3, and when you increase the energy pulse, it's like the reservoir of type 3 is like is empty, and you favor only the thermal type 1, as it's like you could only make disappear the type 3 in contrast to the thermal type 1. I don't know if I know that usually you go to the type 1 to the type 3, but in this case, I don't know if it's due to the wavelength that we used, but whatever the repetition rate, to observe the same evolution on the modification that we can observe.
Yeah, but I had the same problem before having thermal tape 1 plus bubble, the periodic. I had the same problem with the zinc phosphate before. That's why I'm asking if you have any answer, just to know, because I'm still curious about what's happening.
Yeah.
Okay. Thank you.
Thank you, Alain.
Thanks, Alain. Any other question? If not, I will thank Theo for this presentation. Our next speaker is Mathieu Belec.
If I do this, tac. Okay.
Mathieu Belec, stage is yours.
Your screen sharing is paused. Right at. Resume share. To stop share, I will make the desktop directly. Okay. 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 It's okay.
Okay. Thank you very much for the introduction, Younes. So I'm Mathieu Belec. I'm CNRS researcher at the Institute of Physics of Nice in France. And today we'll be presenting some of the results obtained during my stay here at COPL last year in the group of Martin Bernier and Réal Val. So maybe just before starting, I really want to thank all the people involved in the organization of the FunGlass program, both and mainly at Bordeaux and the Quebec sites. So Lionel, Vanessa, Younes, Réal, and Martin, really thank you. I had a chance to go and to do a mobility from France to Quebec, and it was really a fantastic professional and personal and family experience. So really thank you for make this possible. As you see, I have different affiliation, and that's why this is due to the mobility. So I guess you know the scientific environment at Bordeaux centers at COPL. However, I'm working at the University Côte d'Azur in Nice, in the Institute of Physics of Nice. So we'll just take like 1 minute to make a short overview of what we are doing there. Our institute is like 150 people big, and it's organized along 3 main research axes and supported by 5 technology platforms. And it's quite interdisciplinary. We are working on waves and quantum physics, on photonics, and on soft matter. And if we have a small focus on photonics at the institute, there are 5 research teams working on fiber optics and applications, complex photonic systems and materials, quantum photonics and quantum information, waves in complex systems and cold atoms. And there are some dedicated technology platforms on optical fiber fabrication, integrated optical circuits fabrication in lithium niobate, and also other equipment, lasers and detectors for optics and photonics for light matter interaction. And a bit more specifically, the group I'm working in is waves in complex systems, and there I'm in charge of a research line on photonics in laser structured complex media. And actually one of the central tool I'm using is direct laser writing technology. So we just start by presenting you this technology. We earned that already in the previous talks. The principle is quite simple. You just strongly focus an ultra-short laser in a transparent material, like a glass, and via nonlinear processes, we'll come back to this later, you can get some local modification at the microscale or even less. Now, if you move your sample, you can induce some larger scale modifications up to a few centimeters, a few tens of centimeters long. And the main advantages of this technology for photonic devices fabrication is the fact that you can get some local modification of the optical properties. So you have a 3D capability. You can use it in a wide range of optical material, optical glasses. And it's a single step, almost single step, maskless technology. If you want to get more insight on the laser and the experimental parameter to use, you have to have a look on the laser matter interaction involved in this process, from photon absorption to material modification. And it's usually divided in 3 steps. The first one concerns the carrier excitations following the absorption of photons. Then these carriers thermalize and transfer the energy from to the glass matrix or material matrix. And then you get some thermal and structural events, and you end up with some material modifications. So there is here the time scales, the time scale of such processes. But what you have to keep in mind is that absorption is almost instantaneous, but the full process takes like microsecond scale. Now, we've seen it previously. I will go fast on these slides. One of the key parameter and key process is the absorption of photons. So we can have a very simple sketch of the band structure of the glass with valence and condition bands. If you shine it with a UV laser, you get a linear absorption. However, if you shine it with an infrared laser, as we do in direct laser writing technique, it's almost transparent. So you need very high intensity to simultaneously sum up infrared photons to get some absorption and to excite your material. So since it requires some very high intensity, this process is very highly localized, as shown on this graph, which shows the intensity of a Gaussian beam, which is strongly focused. So maybe to get some typical numbers, you get such kind of process for very high intensity, like 10 to the 14 watt per square centimeter. So it's a huge intensity. You need very high peak power. That's why you need some 100 femtosecond pulse in the infrared. And the energy is about 1 microjoule typically, and it has to be focused on like 10 micrometers square. Now there are many different parameters to be controlled in order to modify the material to reach the damage structural intensity. And as we see on this graph here, actually the threshold intensity doesn't depend a lot on the band gap of the material. You see a different threshold intensity for different material. So it's almost the same, very close value. It's the same for the pulse duration as far as you are in the hundreds of femtosecond pulse. Of course, the focusing system is very important. The numerical aperture will be very important, and you have to control accordingly the pulse energy. So for very high numerical aperture, you need energy like you can modify your material with like few tens of nanojoules. Whereas if you have very low numerical aperture, it's this region here. In that case, you need like microjoules. So then it involves some different laser technologies, and there are some consequences. So you have to take this into account. Other parameters you can change are the repetition rate, and more or less similarly the writing speed velocity, the writing velocity, sorry. And depending on this parameter, you get really different behavior as depicted in this image. On the left, you get a single pulse track and modification of glass, and on the right, you are with the same energy, but with much more pulses and with very high repetition rates. And what you have to keep in mind is that, again, this typical time scale of the process. So if you want to get some accumulation effects, you have to be like you have to get a repetition rate larger than 100 kilohertz typically. Then we've seen it already. If you vary the pulse energy, you get three types of defects. At low energy, you get like isotropic defect and isotropic modification of the material, of the refractive index. At intermediate energy, you get some birefringent structures with nanogratings and so on. And if you go at higher energy, you get some microvoids, as we've seen previously. So it's type 1, 2, and 3. It's not written here. So if you manage to tune all these parameters, you can fabricate some complex photonic circuits based on waveguides, as shown on this background image. You see some kind of lines. There are some coupled waveguides that are arranged and spaced by typical distances here, 20 micrometer. And the parameter used for such kind of application are shown here. So you get a laser at 1 micron wavelength, 150 femtosecond, 200 nanojoules, numerical aperture of 0.5, 1 megahertz, and a writing velocity of 10 millimeter per second. So these are really typical parameters to write some homogeneous waveguides. And it's now done kind of routinely. You can get single mode, low loss waveguides that can operate from the visible to the mid-infrared. And it's used in a broad range of applications, ranging from quantum photonics to analog simulators, sensor devices, displays, etc. Actually, most of the attention has focused on bulk systems, but you can also use this technology to write some photonic structures directly in optical fibers. There are different kind of structures you can write. We've seen it in the very first session of the Fenglas days. You can use this tool to fabricate some fiber Bragg gratings. So the idea is just to write some periodic structure of the refractive index directly in the core of the fiber. There are different techniques. Either you do it point by point or in a single step using a cylindrical lens and a phase mask. You can also use the laser to write some optical circuits and optofluidic circuits directly in the cladding of the fiber. It's shown on this image here, and I want you to pay attention on this picture, where you see the cross section of the optical fiber, and in white you get the core, and just on the left you get some waveguide which has been inscribed by femtosecond laser. The distribution is quite elongating and very inhomogeneous, and it's more or less the state of the art of the waveguiding writing in optical fiber. I will come to that later. You can also use direct laser writing in another way, using two-photon polymerization to add some functionalities directly on top of optical fibers. And one point is that the current technology limits the fabrication to very localized photonic structures. And one of our motivation during this project was really to fabricate some longer, let's say, arbitrarily long and complex arrangements of core or of photonic structures directly in optical fibers. There exist some approaches. You can use multi-core fibers, either coupled or decoupled, but it's not that easy to fabricate. And you can directly make some structuring of the optical preform using, for instance, 3D printing techniques. One of them has been developed here at COPL. But yes, this is the very beginning of the research on this topic. So we decided to go with another approach, which is to develop another innovative laser writing technique to achieve this goal and this kind of structures. So yes, to do so, we actually combine the phase mask technique I just presented, which is routinely used for fiber Bragg grating writing. So we combine such kind of technique with a reel-to-reel setup, which has been only sparsely used for fabricating some anon scattering fibers. So the principle is here on the left. You come with a coreless fiber, you translate it directly in the path of the laser, and you collect it in another spool. So this kind of reel-to-reel setup allows you to write, in principle, some arbitrary longer structure. We use an infrared laser, so as said, we can process a broad range of optical glasses, and more importantly, we can process directly through the coating of the optical fiber. We have here on the right a detailed view of the focusing system, which uses a cylindrical lens and a phase mask, and it allows really to distribute the optical beam on a very elongated focal zone and with thousands of small spots. So it allows really to speed up the processing and to mitigate the multifilamentation process that might occur in these situations. Yes, this is how the experimental setup looks like. You get here, you have a small white line, it's optical fiber, and it's displaced using spools and pulleys. The laser is coming from behind and across a cylindrical lens and the phase mask. In this study and in the work in the result I will be presenting, we used a pure silica optical fiber with it's coreless, and the diameter is 125 micrometer. It's accurate coating, and everything is home-drawn. The femtosecond workstation we used is a source emitting at 800 nanometer, 30 femtosecond, like 1 kilohertz, and about more than 200 microjoules. So it's quite unusual to write waveguides in fused silica using this kind of settings. I told you that usually you need to get very high repetition rate. Here it's quite low, it's 1 kilohertz only. And if you would use such kind of workstation to write waveguides in fused silica, it's possible, but it's very, very, very slow. I mean, like tens of micrometer per second for the writing velocity. And in that case, as I will show you, we managed to write at acceptable velocities, like about 1 millimeter per second. So here are the results. So we write some, in this case, just for the analysis, like 10 or 20 centimeter long waveguides directly in optical fiber, and we managed to measure the transverse profile of the refractive index modification. So this is the top left image here. What we see, and it has to be compared with the image I've shown you in the introduction, is that we get something very much more homogeneous and circular. It's also quite reproducible. On the right here, you get the X profile of the refractive index for 6 independent realizations. And we got similar profile and similar value. We also measure the longitudinal profile using a wavefront sensor. In that case, it's also very homogeneous, at least on this scale. And another important point is that we can control the refractive index modification as expected by changing the writing velocity. So if you focus on the blue curve here, this is yes, the refractive index modification for different velocities. So yes, it decreases as the velocity increases. And we also have the possibility to load the fiber here with hydrogen in order to increase the photosensitivity. And in that case, we see a non-negligible increase of the refractive index. And I will also come back to this later in the conclusion. So before going to the analysis of the modal properties and the waveguiding properties of this waveguide, I just want to show you some results about the system stability of this technique, because it's not usual. We use pulleys, and I mean it's not at first look it looks not very stable. So let's have a more careful look on that. So on the left here you get the central transverse position of various waveguide inscribed in similar condition. The cross here corresponds to the center of the fiber, and the center of the circle corresponds to the average of this point, and the radius corresponds to the standard deviation. So what you can conclude here is that our system is accurate. We are very close to the center, but not precise, and not very precise. So to understand where these fluctuations come from, we measure the fiber transverse displacement during the writing procedure. And this is the top graph here, where you see the displacement along the X and Y axis, blue and red respectively. And you see that we have different scales for the fluctuations. The bigger one fluctuates from plus or minus 2 typically, so even a bit more. So it's very similar to the fluctuation we observe on the left figure here. There are also some other scales like plus or minus 0.2 micron, but this can be compensated by changing the tension in the fiber and so on. But yes, the major problem is that, and we still have to identify it clearly, is that the fiber is moving along while it's displaced. However, it could be optimized using an image processing procedure of auto positioning, as reported in this recent paper. We also measure the plasma intensity that is emitted during the writing of the waveguide. So in gray, you get background noise. So we just integrate such kind of zone. We just image the plasma, and we integrate all the region of interest with and without the writing laser. So in blue, it's with the laser. It's again, there are some fluctuation, but it's more or less constant, except for some spikes, as you can see here at 300 millimeter and something. In that case, you don't get any plasma anymore. So it means that the laser doesn't shine correctly the waveguide in the fiber. So you don't write any waveguide. It might be due to dust on top of the fiber. Again, this has to be corrected and understand. But as you will see, the overall properties are not that affected. Yes, so I will come now to the transmission measurement. So in that case, we wrote like 4 meter long waveguides, and we used 2 devices to measure the transmission: a supercontinuum source here at the bottom of the image, and an optical spectrum analyzer at the top. And in between, okay, it's not easy to see, but you get an optical fiber with a laser written waveguide inside. So if you look on the graph, what you see in gray is the signal at the output, the spectrum, the output spectrum, when we inject light directly in the cladding. So we don't put the light in the written core, and this is done with the blue curve. So what you see is that you get an operating waveguides in the visible and the near infrared, with, in this specific case, an optimized value at like 900 nanometer. So we measure the properties at this wavelength. It's worth mentioning that here we observe a slight dip at 765 nanometer, And it corresponds to the second order of the reminiscent FBG that we write in this kind of waveguide. Remember, we use phase mass to write this kind of waveguide, so it's supposed to operate. I mean, when it's used in a fixed configuration, it's supposed to write a fiber Bragg grating. So this is the second order of this kind of a Bragg grating. On this image, we measure directly the intensity of the mode at nitrogen nanometer. We have something which is again quite intense, highly single mode, and almost circular. And to finish with that, we also measure the transmission for different lengths of the fiber. So we just did a cutback method. So we start measuring the transmission after the 4 meters of the fiber, and then we cut the fiber like a piece of 20 centimeter, and we obtain such kind of results, which is, I mean, the error bar is included directly in the markers, so we get something like 0.14 dB per centimeter, which is quite good if we consider direct laser written waveguides in glass, but which is still too high for our purpose, which is to write some meter-long waveguides. So I will conclude with that. We developed an innovative direct laser writing technique. We managed to really write for the first time very long waveguide, which are low loss and single mode, and they operate in the near infrared. We can control the value of the refractive index, which is quite smooth and quasi-circular in terms of the cross section, and we can also use on the loading to have a good control on the refractive index. The work in progress concerns highly photosensitive optical fibers that are doped with germanium. So the goal is to increase the refractive index to operate in the telecom with lower losses. So we can see here on the right some results, and with a germanium doped optical fiber, you see that the refractive index is highly enhanced. In this case, we still have a lot of losses, so we have to find some tricks and to some annealing procedure to remove or decrease the natural losses. And this is a work in progress. As an outlook of this work, we plan to inscribe some advanced components like maxillary interferometer, helicoidal core for long period gratings, more complex lattices. We also want, and it's also work in progress, to exploit the weak continuous distribution of FBGs for random fiber lasers and distributed sensors. And yes, we will also use this technique in novel kind of optical fibers, as the one presented by Theo previously, and ultimately deploy that on a fiber draw tower. So with that, I just want to acknowledge sponsors and people, principally and mainly the COPL colleagues that really help with fruitful discussion and technical support, and more particularly Réal Vallée and Martin Bernier for welcoming me in their group. And I want to thank you for your attention.
Thank you, Mathieu. If we have any question. Chat. Let's see if we are here.
Okay.
Réal, no.
Mathieu,
Yes.
what is the ultimate source of losses that we have to fight against if we want to reduce it to dB per meters? Maybe you can repeat the question.
Repeat the question.
Yes. Réal asked what's the ultimate source of losses in this system if we want to really decrease it up to dB per meter. And this is a good question. If we strongly doped with germanium, we'll get some if we make some hydrogen loading, we can really increase the refractiveness as shown on the last slide. But we have strong loss due to OH center or something like that. So the plan at short time scale is to anneal the fiber using a special coating, because we tried it already. We can reduce the losses, but we have problem with polymeric coating. So we have to use, let's say, a stronger coating that resists to temperatures. It was like 400 degrees, something. Yes, polyimide coating. So this is a very short time work we plan. Okay.
Matthew, I have one question.
Yes.
Yeah. You show us today you make your grating in horizontal in the lab scale. Now, in the future, what we are looking is to make it in drawing tower. You don't think that the challenge will be more when we are going to drawing tower and start writing?
I would say it's, I mean, from a, yes, it's a really long scale perspective, but it should be only a technical problem. I mean, just to switch to rotate the setup.
The setup from horizontal to
but technical problems that can take long.
Okay, step by step.
Step by step.
If there are not any other question, let's thank Matthew again. Let's move to our next talk. Last one this morning.
It seems that there is no
display
anymore.
Yeah,
No,
I think the camera is not working properly. I really don't know why, but okay.
Thanks to our colleague Alexian Wang. I would like to thank him because I asked him for the last minute. Alexian, he's senior researcher at Huawei, Quebec.
I just need to download
In Quebec City.
I guess it's this one.
Yeah, please. Alexian.
Okay. Can you see our screen? I guess it's okay.
Okay, so I just pressed.
Yes. Yeah, I think so.
Great. Hello everyone. My name is Li Shen Wang. I'm from Huawei Technologies, Canada, and the lab in Quebec City. We are right here. So today I'm going to talk about the fibers for future telecommunications. I know that this program, Fun Glasses, is mostly for material guys, and for telecommunication, it's a bit far away from material society. So, but currently there is a trend that the telecommunication is moving, it's like turning a U-turn back to the material physics or chemistry. So today I'm going to talk about how the telecommunication is linked with the material. And before I start my talk, I just give a brief introduction of myself. I got my PhD in 2011 in Institute of Semiconductors, Chinese Academy of Sciences, in physical and electronics. And from 2011 to 2013, I was an assistant researcher and then an associate researcher in the same institute. And since 2013, I joined
Center of Optics, Photonics, and Lasers, University Laval here as a postdoc fellow, and then a research associate. And since 2016, I joined Coactive High Tech as an R&D scientist, working on the high power fiber laser. And 3 years ago, I joined Huawei Technologies Canada as a senior staff engineer. Currently, I'm the leader of the fiber amplifier team in Quebec City. So my research interest currently is the optical amplifiers. So optical amplifiers, in fact, is the building block of our optical communication system. If you look at this picture, from Beijing to Shanghai, the two major cities in China, the distance is around 2,000 kilometers. And currently we have a lot of data traffic between the cities like this, and we use optical fibers to transmit the data. And since the fiber is very, very long, we need amplifiers to regenerate the signal, to compensate the loss induced by the silica fiber. Then we need optical amplifiers. And in fact, the optical fiber, silica fiber, plus the optical amplifier, fiber amplifier, is the basis of the optical telecommunication systems. So for optical fibers, as we all know, Dr. Charles Scow, he got the Nobel Prize because he has found this amazing material for a very low loss and a very wide bandwidth transmission. And also the amplifier, mainly the erbium doped fiber amplifier, the EDFA, was invented several decades ago by David Payne in Southampton. I believe one day maybe he will also won the Nobel Prize. So our task here is to explore advanced fiber amplifier technologies to support higher capacity of future optical communication systems. So why amplifiers? Why we go back to materials? In the past decades, since 2000, I mean 20 years ago, the driving force of the development of telecommunication systems are twofold. In fact, the first is that because of the invention of EDFA has provided us a very wide bandwidth, amplification bandwidth, about 8 terahertz, about 80 nanometers if we talk about wavelengths. So this gives us plenty of bandwidth for loading data. And the second building block or second driving force for development of telecommunication is the microelectronics chips that has provided us amazing, huge amount of calculation capacities. So in the past 20 years, especially from 2009 to 2019, the past decade, most of the telecommunication people are working on developing algorithms, digital DSP, digital processing algorithms to improve the performance of telecommunication, like using coherent modulation format, like nonlinear compensation, or done in computers, in microelectronics. So, but until 2019, these two resources are kind of being exhausted. Firstly, in terms of EDFAs, we use the so-called DWDM, dense wavelength division multiplexing technology. We put a lot of different wavelengths, stuck it into the bandwidth of EDFA, and currently it's full. And the secondly is the DSP. We have people have developed a lot of algorithms, new strategies, but they currently it's kind of all the methods has been kind of used. We are running out of resources. Give you just an example. For currently, like my colleagues in Ottawa, they maybe a team of 20 people. They work for 1 year, and the optical signal noise ratio can only be improved by like 0.2 dB. And this is so they are going to be fired. So it's really to the limit. We call it the Shannon limit. We already close to the Shannon limit of the transmission capacity. So now people are now looking for new resources. Then we go back to materials. We go back to the history. The boosting of telecommunication of the boosting of our internet is mainly because of the invention of silica fiber and EDFA. So now we are thinking, do we have new materials that can open a new era? So this is why we open a lab here in Quebec and start the research in glass materials and the glass materials that can serve better amplifiers. So here is this figure shows the here in the following I will introduce some of our work. So here this figure shows the transmission spectrum, loss spectrum of the silica fiber. You see that in we call the C band and L band from 1.5 micron to 1.6 micron in this region, the loss is the lowest. And luckily, the erbium emission bandwidths superimpose with this very low loss region. So like 30 years ago, since the EDFA was, when the EDFA was invented, the EDFA can easily provide in total about 8 terahertz bandwidths, 4 terahertz in the C band and 4 terahertz in the L band. So this EDFA has served for more than 25 years. And then recently, since 2018, Huawei Technologies in China and also in Canada, we invested a lot of energy, a lot of resources in the material, in fine polishing the silica-based erbium doped fibers, the materials, to play with the co-dopants, the fabrication process, and then we successfully expand the bandwidth of erbium in the C band from 4 terahertz to 6 terahertz. That is 50% of increase. And then we move our site to the L band. So since 2019, we start to work on in the L band. We want to expand also, copy the success in C band. We want to expand the bandwidth in L band. Then this is again about the material, because usually the erbium doped fiber is the glass matrix is aluminosilicate glass. But the erbium in the aluminosilicate glass, the emission bandwidth is very limited. It's limited to 16-15 nanometers. Beyond that, the gain drops very fast. So we try to explore new materials. Then we move to phosphosilicate glass. This can extend the amplification bandwidth from 16-15 to around 16-20 nanometers. So we called it the extended L band. For this work, we have a close collaboration with the team of Professor Younes Messadek in Ethiopia and Sophie La Rochelle, also in Université Laval. And after we fine polish the glass matrix, currently we call the era of super air. Now we could expand also the bandwidth in the L band to beyond the 16-20 nanometers to support, which can support 6 terahertz. So it's the same as what is now in the C band. So the key,
the key point behind this development is that we need to understand better and manipulate better the interaction between the glass material and the erbium ions. In our recent researches, we found that this interact is in fact very tricky. And most of the time, what we can do is just try and error. But I think there must be physics behind it. So maybe this could, our further work could reveal something new to the society, not only the academic one, but also the industrial. And in addition to the erbium EDFAs for C and L band, currently telecommunication people are looking for possibilities of using the S band and E band, which is located in between 1.4 micron to 1.5 micron. So again, in this wavelength region, erbium can't work. So currently we are working on the bismuth. The bismuth doped fiber amplifier was invented back in 2006 by the famous Professor Dyanov, who has passed a few years, 2 years ago in Russia. And bismuth is an amazing ion. Although the physics behind it is not 100% revealed yet, but people has currently successfully managed to, has found ways to make fibers that can show promising amplification performances. Based on our recent research here in Quebec, we found that the bismuth-doped fiber amplifiers, if assisted by the erbium-doped amplifier, it can provide more than 90 nanometers amplification bandwidth, covering the whole E and S band, and the output power can be well above watt level, and the noise figure, based on my calculation recently, can be very close to the quantum limit of 3 dB. So here we have a collaboration with Professor Younes, and we are working on developing the glass materials, glass fibers that can make the best use of the spectroscopic property of bismuth active centers. And this is in fact, this is very tricky. There are lots of, the bismuth is not as stable as erbium. It can be infected by many factors, like the temperature of the temperature, the gas flow, the drawing speed, everything. It's a very challenging work, but we have shown very encouraging results until now. Okay, so that is the material side, and on top of that, another degree of freedom to further expand the capacity of telecommunication system is the space channels. So some people say that why don't we just focusing on the region where the amplifier performance is best, namely the C and L band, then we use the space channels. Space channels means multiple fiber lanes or multiple fiber cores in one glass clad, or multiple spatial modes of a multi-mode core. And this is similar to the microelectronics that nowadays we use multi-core processors. So by using multiple space channels, we could further increase scale the capacity. And this, in fact, go back to materials, is strongly dependent on how we could manipulate the glass fibers, make smaller, more compact, user-friendly fibers, like multi-fiber array, multi-fiber doped fibers, and the few mode fibers. For example, the few mode fibers, we need to finely control
the refractive index profile, doping profile, and finally control the erbium doping profile within the core. And this is very critical to the performance of that type of fiber. So, and also the materials like the multi-element fiber, erbium, ytterbium doped fiber. Erbium, ytterbium doped fiber favors the low-cost cladding multi-mode pump like in 915, 945 nanometers. And the low cost is very critical for using these space channels. So this also goes to the fiber design, goes to how we manipulate the fiber fabrication. What is the optimum glass materials? So yeah, that's all about our work and how it is linked to the materials. Thank you. Thank you very much.
Introduction.
Yeah.
If there are any question, can see any question here. Let's see if there are the
Chat.
chat. Yeah, let's see if there are anything in chat.
What?
Nice to everyone. Don't have any question for now.
No? Okay.
A question?
No
Can I ask a
questions?
question?
Yes.
Alexian?
Yes.
Yeah. When you are saying that the basement then will cover for the S-band, then the S-band will be also, it's another avenue for,
The S-band.
yeah.
Yes, of course. In fact, if we go back to the most probably the first band we will use is the S-band. From C, L, and S-band, and then maybe E-band. And then finally, then U-band maybe also. U-band.
Yeah.
And in O-band, it's all for other application. For E, S, and CL, these are for long-haul telecom. For metropolitan network, some people use, in some application scenarios, they use O-band at 1.3 nanometers, 1.3 micron, sorry.
But for that, we need to develop new compounds like lasers and everything. If
lasers are already there because semiconductor lasers, they can cover very wide range. So semiconductor lasers are there. Laser sources are there for modulators. We have it, lithium niobate and of indium phosphate, and we have modulators. Detectors, semiconductors can cover that. So the missing part is the amplifier.
okay,
Yeah.
then if you said based on the work of Dianov, if there any work have been done using the fiber of Dianov and some amplifier have been tested, or?
Yes. In fact, the O-band amplifier is already productorized by OFS 2 years ago. Last year, 2 years ago, yes. They already have a commercial product for the amplification in O-band.
Okay.
Yeah.
And it is promising. What is?
Yeah, this is very promising. Currently in O-band application, they use semiconductor amplifiers, but because the carriers in semiconductor amplifiers have very small lifetime, so when we call it on-off key, that is the bright and dark communication. There will be because of this very short lifetime, when the OOK frequency is very high, the semiconductor amplifiers will induce significant pulse shape distortion. But with the bismuth doped fiber amplifier, because the lifetime is on the order of several hundreds of microseconds,
yeah.
So it's this kind of effect doesn't exist.
So the performance is better. Yeah, the performance is better. Yeah. Okay.
No, any other question? Okay, let's thank Nixon again. Thank you.
Yeah, just as I said in the beginning, I would like to show you 10 minutes of a video to show you the activity of our lab and different equipment. And just to let you, this video have been produced by our student in the last 5 days. I would like to thank them very much because they are very extensive and interesting work.
The research program at UNES Mesadec Laboratory is focused on the development of a new generation of materials for optics and photonics, such as new optical glasses, glass ceramics, and optical fibers based on heavy oxide, phosphate, telluride, and chalcogenide glasses. For years, UNES Mesadec Laboratory has been tailoring materials to provide unique emission spectra, nonlinearity, magneto, electro-optical, or thermomechanical properties. More recently, the group has concentrated efforts on elaborating new glasses with a wide transparency window in the mid-infrared region for a new generation of optical fibers and amplifiers. Professor Mesadec's laboratories are located at the Center for Optics, Photonics, and Laser, the COPL, at the Université Laval in Quebec City, Canada. The center has 107 laboratories and 5,000 square meters of Class 5 clean room. The temperature is controlled in each laboratory all year long. The most sensible laboratories are located underground to minimize mechanical vibrations. In addition to state-of-the-art equipment for optical fiber manufacturing and preform fabrication, the laboratories are equipped with sophisticated optical testing and measurement instruments. In this video, we will guide you through Professor Mesadec's laboratories at the COPL's facility, starting with the glass preparation laboratory, followed by the preform fabrication laboratory and fiber drawing tower. Finally, we will show you some laboratories dedicated to the characterization of materials. In the oxide glass laboratory, heavy oxide, phosphate, and telluride glasses are prepared by melting high-purity precursors and then quenched in molds according to the application. The variety of furnaces allows the melting of glasses ranging from a few hundred to 1800 degrees Celsius. A glove box equipped with multiple furnaces is used in applications requiring a refined control of the atmosphere, such as glass compositions where the purity is critical and precursors that are sensitive to environmental humidity. Chalcogenide glasses are known for their transparency in the infrared region, up to 20 micrometers. Professor Mesadec's laboratory is the unique research facility in Canada able to produce high-purity chalcogenide glasses and optical fibers. Everything starts with the ampoule fabrication, which is made by our research personnel for each specific purpose. The precursors are distilled, redistilled, and stored in a dedicated glove box. When a researcher or a customer needs a glass composition, these precursors are weighted and a purification setup is assembled. The glasses are melted in a rocking furnace for several hours to guarantee their homogeneity. Each glass composition can be distilled up to 3 times to ensure its purity and transmission in the infrared region before being drawn into a fiber. At the frontiers of materials innovation, new organic glasses and hybrid materials are developed in the Sogel laboratory for functional coatings, which can be applied by a deep coating machine developed by our team. These materials can also be 3D printed using a multi-wavelength stereolithography printer developed by our PhD researchers and technical staff. In the modified chemical vapor deposition process, also known as MCVD, precursors with ultra-high purity are deposited in the inner part of an equally high-purity silica tube to build a preform which will be drawn into an optical fiber. The volatile precursors will form the core of the fiber, whereas the tube will form the fiber cladding. A controlled mix of volatile precursors of aluminum, phosphor, silicon, and germanium allows the precise control of the optical properties of the fiber. As the mixture is heated, it forms a deposit known as soot. The tube containing the soot is thermally treated to convert the porous soot into a glass layer. This step is followed by the tube collapse. The preform is almost ready. After cutting, the preform can be drawn into a fiber. Professor Mesadek's laboratory has the know-how for drawing any kind of optical fiber, from mid-infrared fibers such as telluride, galates, and chalcogenides, to polymeric and microstructured fibers, as photonic crystals and multi-core fibers, as well as the more common silica fibers. 2 fibering towers are installed in a laboratory dedicated to the research in fiber drawing. An 11 meters tower is dedicated to silica fibers with a graphite furnace able to reach 2200 degrees Celsius. Here, we observe the first drop flowing at the beginning of the drawing. The filament that comes just after it will form the optical fiber. The fiber diameter is closely monitored along the process and controlled by optimizing the temperature and drawing speed. A double polymeric coating is applied to protect the fiber, improving its mechanical resistance. On the second tower, non-silica glasses, also known as exotic glasses, can be drawn into fibers. We have a set of 4 furnaces at hand to choose the best drawing conditions. For example, a double crucible furnace is frequently used for chalcogenide fibers, where molten core and cladding glasses are inserted one into another just before drawing. For compositions prone to crystallization or chemically sensitive, a furnace with a controlled atmosphere is put in place. The thin film deposition is performed in a hybrid evaporation system, containing an electron beam and a thermal evaporation source. Therefore, glass compositions otherwise difficult to obtain can be formed by co-evaporating materials. The wide chamber fits not only usual substrates such as glass slides and silicon wafers, but can also be used for substrates up to 60 centimeters wide, like mirrors and even preforms. Our research group counts on a variety of laboratories for characterization and material analysis focused on the optical, mechanical, magneto- and electro-optical properties of crystalline and amorphous materials. The laboratories are equipped with a range of instruments for the characterization of advanced materials of high and low dimensionality. Optical fibers and bulk classes are characterized using a different set of equipment and techniques. We use an ultraviolet visible near-infrared spectrometer to measure the light absorption in bulk samples and thin films. Vibrational spectroscopy is performed in a Raman confocal microscope equipped with multiple laser sources and able to map samples at a submicrometric scale. Our group also possesses a high-resolution prism coupler for measuring refractive indexes. An accessory can also be used to couple the light in thin films and measure its refractive index and thickness. We assembled a spectrofluorometric platform for steady-state and time-resolved fluorescence measurements up to 4.5 microns at room and cryogenic temperatures. A large set of accessories allows the measurement of optical fibers, microscopic, liquid, and bulk samples. Our laboratories are equipped with a variety of optical microscopes and with a scanning electron microscope that permits the microstructural characterization of the materials with high-quality images. With decades on expertise in optical materials, our group has been actively collaborating with industrial partners and research teams around the globe. Beyond the optical research, our team is also working on other frontiers of science, like smart textiles for healthcare applications, wastewater treatment, optogenetics, and a new generation of semiconductor devices.
Okay. Thanks for.
Allez. Elle est gigantesque. Elle est vraiment gigantesque. Elle rentre même pas dans le cadre. Oh, vous savez quoi?
Ah oui.